where's my share? There we go.
It's remembering all of the different angles and bond versus bond pair and lone pair combos, like like just to remember all of those.
It's actually not difficult at all because you only have what, four bond angles. You got 90 degrees, you got 109.5, and you got 120 and 180. So 5 angles. That's all you have to remember. 4 angles. And it's not bad at all because 3 of the angles you can easily demonstrate by drawing a circle. Only one of them is difficult. So let's look at something called electron pair geometry. And remember, if you have trouble remembering it, you can, for the test, put it on your card, right? So electron pair geometry. This is what VESPER is based on. So the idea is that electrons around an atom, a single atom, one atom, all the electrons around that one atom repel one another. And they try to get as far away apart from one another as possible to reduce repulsion. So when we look at electron pair geometries, we have 5 of them. So here's your central atom, and this is a pair, and this is a pair. And to get as far away apart from one another, they're going to be on opposite sides of the atom. We call this linear, and the angles are 180 degrees. Because we know from sports that if you do a full circle, it's 360, right? So what if you only do a half circle? It's 180. And it doesn't matter which side we do this on, it's 180. The next one is this one here. I call it the triangular propeller, but it's called trigonal planar. And here, a full circle is 360 degrees. So if you divide it into 3 equal parts, it's 120 degrees. This is the tough one. This one's called tetrahedral. And the angles are 109.5 degrees. So if I pull out my kit here, I can show that to you. Show that to you right here. So can you see the 4 pairs? 1, 2, 3, 4.
Yeah.
Okay, so here you can see that with the 4 of them, it's shaped like a 3-legged stool with a little top on top of it, right? So 3-legged stool with the top, tetrahedral 109.5. And you can see the angle here is greater than 90. And this is better than this. Because here, the angles, when they are perpendicular to one another, we call them right angles. And you can see that the angle between these right angles is smaller than the angles here. And smaller means closer together, which means more repulsion. So what's going to be better? Having them separated all apart like that, or have them in a plus sign? And the answer is having them all apart. So tetrahedral. Now, what if you have 5? If you have 5, it looks like this. So it looks like the flat triangle, right? But I only have 3 attached. Now I'm going to attach the 4th and the 5th. So what you're supposed to see here is something that looks like there are 3 pairs around the circle or equator and 2 that are opposite one another. So you can think of this as like the Earth with the North Pole and the South Pole and the equator. So how do you draw this? Well, here's the opposites. And here are the 3 around the equator. And these positions here are actually called axial, because they're like the axis on a car or the axis on the Earth. And these are called equatorial. A lot of people say equatorial. It's not, it's equatorial. And the reason we know it's equatorial is because the position is based on equator, which is QUA, not equator, right? It's not the equator, it's the equator.
Yeah.
This shape is called trigonal bipyramidal. Some people just call it bipyramidal. Our book may do that. I don't. I like trigonal bipyramidal better. And the angles here are 90 degrees, 120 degrees, and 180 degrees. And if we take a look here at this molecule, can you see that these 2 that I have my fingers on are 180 degrees apart?
Yeah.
Can you see that these 2 that I have my finger on are 90 degrees apart?
Yeah.
Can you see, looking from the top, that these 2 that I have my fingers on are 120 degrees apart?
Yeah. So on your drawing, where is the 120?
Well, it's on the equator, so it's kind of hidden, as it were. It's kind of like this. Do you see this?
Yeah.
This is what my drawing is. This right here. Where's the 120 degrees?
Is it the one closer and farther?
This one and this one, right? These 2 right here, right?
Yeah.
But also these 2 right here that are in the back.
Okay.
Whoops. And these 2 right here are 120.
Okay.
So if I do something like this, so if I change them so that the white ones are axial and the green ones are equatorial, where's the 120 degrees? It's between any 2 of the green ones. And when we see it from above, it's easier to see, right?
Yeah.
But if we do this from above, where's the 180?
The axial?
Yeah, but you can't see it, can you?
No.
So you have to use your imagination with these. That's all there is to it. No way around it. So you have to be a visual learner. Now, what happens if you have 6? If you have 6, it looks like this. It almost looks like a dragonfly where this is the head, this is the tail, and here are the wings. And that's this guy right here. So what are the angles here between the top and the bottom?
180.
Okay, what are the angles between the top and one of the side ones?
Would it be 120?
Let's take a look. What does it look like?
Maybe 90?
Well, do they look like they're perpendicular to one another?
I guess.
So perpendicular means a 90-degree angle.
Yeah.
So perpendicular means like the edge of a square.
Mm-hmm.
So that does look like it's squared off, doesn't it?
Yeah.
So 90 degrees. How about the angle between two of these that are next to each other? Well, the best way to see that is to rotate this. Well, let's take a look. What's the angle between two that are next door to each other?
Would it be 90?
It's 90. So you've got to get a little more comfortable with calling the angles. Perpendicular is 90 degrees, and you just got to memorize that.
I know that.
And the best way to memorize that is what's 90 times 4?
360.
360. So here, if we have 90, 90, 90, and 90, that adds up to 360. That's a full rotation around this circle, isn't it?
Mm-hmm.
So you got to remember a full circle is 360. And when you divide it up into 4 equal parts, it's 360 divided by 4. When you divide it up into 3 equal parts, it's 360 divided by 3. When you divide it into 2 equal parts, it's 360 divided by 2, so that's 180. Now here, this one is tougher because this is not a full circle. There's actually 3 dimensions to the separation. All the rest of these are 2-dimensional shapes, right?
Yeah.
And then when you get to these 3-dimensional shapes, then you have to start thinking, oh, what are the angles? And take a look at that. Is that clear that that is not squared off?
Yeah.
So is it bigger than squared off or smaller than squared off?
Bigger.
So it's got to be bigger than 90. And what's the one other angle we need to memorize other than 90, 120, and 180? 109.5. Right? You know that radio station that you have in Humboldt County, 109.5?
Yeah.
Coming to you from HSU, where they play smooth tetrahedral all day long. And here, this one. Now, this one is called octahedral.
Mm-hmm.
And that's because if you make this model and you drape or connect 3 of the sides or 3 of the pieces and do that everywhere you can, you'll end up having 8 sides. Octa, 8-hedral side. Now, guess what the best way is for you to understand this and to recognize it and to see it?
Get some models.
Models? I would say what could you use for the pairs? Toothpicks. What could you use for the central atom? Carrot. Why would you not use a grape? Because a grape probably would get all mushy with its toothpicks going into it from different angles and it wouldn't hold steady, right? But if you take a carrot, maybe cook it a little bit so it's a little soft, you stick the toothpicks in, you can get that general idea of the shape. Okay? And then if you wanted to say, okay, so the carrot is the central atom, what could you put for atoms on the end?
Olives.
All carrots and olives, an interesting combination, but perfect. Olives, right? Or grapes. Grapes would actually work at that time. Or whatever you have in the refrigerator. Vegetables work pretty well because they have the right tenderness, if you will.
Yeah.
Okay, I wouldn't use hamburger. Now, what you could do also is if you're a teacher of some sort, or you happen to have a bunch of clay around, you could use clay. Clay works pretty good for sticking toothpicks into it. And you don't have to use toothpicks. You could use Q-tips, because Q-tips are toothpicks are really thin and small, right? But Q-tips are a little larger, and you could even cut the Q-tips in 2, so you could use one Q-tip for one side and the other half for the other side. And so Q-tips are a little bigger, so they might be better. But there are many ways to do this without going out and buying a $50 molecular model kit. And it's much cheaper, more satisfying, and you should do this. So these are all electron pair geometries that you need to memorize.
Okay.
So how do you determine the electron pair geometry? I'm going to make this list again, but without the drawings, okay? So I'm writing electron pair geometry. And we're going to go over two things here. First thing we're going to go are, what is a pair? And the answer is the following. If you have an atom with a single bond, that's a pair. And that really makes sense, doesn't it? Because how many electrons are in a single bond? That's a pair. If you have a lone pair, that's a pair. That makes sense, doesn't it?
Yeah.
If you have a double bond, that's a pair. Not two pair, one pair. Because the idea here is that this region of electrons repels all other regions of electrons on that atom. So if we had a lone pair on this side, they would be opposite of one another because you want to reduce repulsion because the pairs are made out of electrons. So here, this is a pair. And you can see why I'm putting these little teardrops around them is because they actually fit with this drawing here, right?
Mm-hmm.
So this is a pair. And why are 4 electrons a pair? And the answer is, here's your double bond. Here's your double bond between 2 atoms, right?
Mm-hmm.
Am I allowed to do this with a double bond and still say it's a double bond? Nope. So those 4 electrons have to stay together so they are one pair because they are one region of electrons that repel other regions of electrons. So we have 2 more pairs. Guess what another one is?
Triple bond?
Precisely. And there's one more pair. Do you know what it is?
Nope.
Can you see it?
Yeah.
A single electron. So these are the things that repel one another. Now, let's look at the geometry. And we're talking about the electron pair geometry, mind you. So I'm going to have a table here that says the geometry and pairs.
Okay.
2 pairs, linear. 3 pairs, trigonal, planar. 4 pairs, tetrahedral. 5 pairs, trigonal, bipyramidal. And 6 is octahedral. Now, the reason this is called trigonal bipyramidal is because if you look at this guy here, so this is the trigonal bipyramidal one. Okay. Now, look at this from the top. Do you see how this one comes out close to you and these 3 are basically a flat base of a triangle? So it's a pyramid, but it's not your normal pyramid. How many sides does your normal pyramid have?
5.
Without including the base.
Oh, 4?
4 sides, right? So here's your regular pyramid right there. How many sides? 1, 2, 3, 4. All you got to do is go to like one of those MapQuest places, look at the pyramids in Giza and do a satellite search and you're going to see 4 sides. It looks like 4 triangles that come together at a peak. So that's a square pyramid, right? So what do you call something that's not a square pyramid, but it's got a triangular base? Trigonal pyramidal. But here, this is one pyramid, right?
Yeah.
Now what happens if I turn this over? What do we have on the bottom? Another pyramid. Bipyramidal, bipyramidal or bipyramidal. And people misspell this one too. They often put an A here, Pyramma. And the way to remember to spell this is just remember the word pyramid. It's pyramid, it's not pyramid, right?
Yeah.
Okay, so here are the pairs and here's the shapes. How are you going to more easily associate the pairs with the shape? Well, here's an exercise we do in class. You're going to be the central atom. So right here, your middle, this is your central atom, and you're going to let your arms be the pairs. How are you going to place your arms compared to your central atom to make them as far away as possible? Go ahead and do it.
Out.
Straight out, right?
Yeah.
And what does that look like? Linear, planar? It's linear, right?
Mm-hmm.
How could you do 3? Well, for 3, you use your arms and your legs. Now, if you stand up straight and you hold your arms out straight, the distance between one arm and the legs is 90 degrees. The distance here is 180. Does that seem fair?
No.
It doesn't. So what if we lifted our arms a little bit? Then the distance between our arms and our legs becomes 120, and the distance between the arms become 120. Boom. That's fair, right?
Yeah.
How do you do tetrahedral? Well, I don't know if you do any sort of like yoga or anything, but to do a tetrahedral, you hold your arms out like this, and you use both of your legs, one leg forward and one leg behind you. And then trigonal bipyramidal, good luck. Good luck. I don't know anyone who can do a trigonal bipyramidal because you could use your head, your 2 arms, and your 2 legs. But you got to imagine that for this one, you got to like take your, somehow make 3 of them like a propeller, 2 arms and a leg or 2 legs and an arm, make them like a propeller. And then you got to have the other 2 things on the opposite sides of that propeller. Good luck. Here, carrots and olives. Okay, so that's the electron pair geometry. Now, there is something called molecular geometry. It's based on the electron pair geometry. So we'll do these one at a time. And when I say one at a time, we're going to do it based on the electron pair geometry. So the first one we're going to do is for a linear electron pair geometry. What does EPG mean?
Electron pair geometry.
Okay, so here, if you have something like this, this is CO2, right?
Mm-hmm.
So if we look at this carbon, it has 2 pair. So this is a linear geometry.
Mm-hmm.
Here's another molecule. If you look at this carbon, it has 2 pair. So it's linear. It's in a linear electron pair geometry. Okay. Let's see. This nitrogen right here, how many pair does it have on it? It's 2 pair. So what's the orientation of the triple bond compared to the lone pair? Opposite one another, linear, right?
Yeah.
Now, what do we call the molecular geometry in each of these? So the electron pair geometry is already linear, but what do we call the molecular geometry? Well, this one we call linear. This one we call linear. This one we call linear. Now, this last one is really a moot point. If you only have two atoms, can they be anything but linear? Can they be in anything but a straight line? Do we ever draw this? We don't, do we? Yeah, you're looking at that like it's stupid, because it is. The electrons would not be up above the atoms. They'd be right between them, holding them together. So this is stupid. So whenever you only have just two atoms connected, what's the shape?
Linear.
Linear. What's the angle?
180.
Okay, so we just got done with the easiest molecular geometry, the one that starts with the linear electron pair geometry to give us our molecular geometry.
Right.
So these match, right? Linear, linear.
Yeah.
Now let's do the next one. So we're going to do a molecular geometry based on a trigonal planar electron pair geometry. So I'm going to give you a few examples. Are you ready?
Yeah.
Here's one. So just like in this one here, we were looking at two pair, right?
Yeah.
So I'm going to put that down here, two pair. So for our trigonal planar, we've got three pair, right?
Yeah.
Okay, does this have three pair?
Yeah.
You betcha. So this is called trigonal planar for the molecular geometry.
Okay.
Now, what are the angles?
120.
120. Here is another example. Now, can you see the pairs on oxygen? The lone pairs on oxygen?
Yeah.
Are they on carbon? No. So do they count as carbon's pairs?
No.
No. So how many pairs on this carbon? The single bond is one pair. This other single bond is one pair. This double bond is one pair. So 1, 2, 3 pair. This is trigonal planar, 120 degrees. Now, what about this guy here? How many pairs are on this guy? The sulfur, that is.
3.
3 pair. But does this look like the triangles that these guys make? If you look at the triangles, this one looks kind of like that. This one looks kind of like that. This one looks kind of like that. It's kind of a flattened triangle, isn't it?
Mm-hmm.
They call this bent. And the reason they call this bent is, imagine your arm is straight out, right? That'd be linear, right?
Yeah.
Now, if I do that, what do we say about my arm?
It's bent.
It's bent. What are the angles? Well, the angles are 120 degrees because it's based on a trigonal planar electron pair geometry, which is 120. The actual angle is not quite 120. It's a little bit different, but you don't need to know it. You need to memorize 120. So here you can see that for this one, for 3 pair, we have 2 geometries, 2 molecular geometries, trigonal planar and bent.
Right.
Okay, so now guess what we're doing? We're going to a tetrahedral electron pair geometry. So molecular geometry based on a tetrahedral EPG. Tetrahedral means 4 pair, right?
Right.
Okay, so here's an example. So here I'm not drawing tiers, I'm drawing lines for bonds. And you see this thing that's called a wedge? That's a bond. Now, whenever you draw a wedge, this is close to you and this is far away from you. The wider part of the wedge is close to you. So it's like art. Here's the sun. Here's a road. Which part of the road is closer to you? The fat part of the road. Which part is farther away? The thin part of the road. Okay? All right. So here, that's what this means. But what does this mean? Well, when you see this, the central atom is close and the other is far. So here that central atom is closer to you, that hydrogen is farther away. So that looks kind of like this right here, where you see this hydrogen is closer to you and this one's farther away compared to the central atom.
Right.
So this is what we do. And, you know, I always tease everyone in my classes that when you draw this, you can see that I have exactly 7 dashes.
Yeah.
And that is not important. How many do you draw? Whatever looks like it fits in there. Fair enough?
Yeah.
Okay, so what do we call this? We call this tetrahedral. And the angles are 109.5 degrees.
Right.
Okay, now here's another molecule. Ammonia. And it's got a lone pair on top. So if this is a trigonal, or this is a tetrahedral, what is this? Because here those electrons don't stick up into space like this hydrogen atom. They're hunkered down on the nitrogen. So what do we call this? We call this a triangle, because when you look at it from the top, excuse me, we call this pyramidal, because when you look at it from the top, it looks like a pyramid, right?
Yeah.
So this one I like to call trigonal because it looks like a 3-sided thing, and pyramidal. And what are the angles?
109.
109.5. They're actually a little bit less, but you don't memorize that. You memorize 109.5 because it's based on tetrahedral electron pair geometry.
So, okay.
Even in my lectures, I make this clear. I say, hey, you don't need to memorize the real angle. Memorize 109.5. That's your prediction. It's actually 107.5. Is our prediction pretty close to reality?
Yeah.
It's within 2%. It's, I mean, I should say it's only 2% off. That's great. Okay, and then there's this one here.
H2O.
H2O. So if we call this guy bent, what are we going to call H2O?
Then
Bent, but is the angle going to be 120?
no.
What are these other angles?
109.5.
Right, so if we go back and you look at all the molecular geometries, if you have the same number of pairs, what's your angle? The same.
So
Here you have 4 pairs, what's your angle? The same. Now this is actually 104.5. It's a little smaller yet than 107.5. And we'll talk about that later, but I don't want to write those numbers down because those aren't the ones you memorize. What do you memorize?
109.5.
109.5. So it seemed like we were on the road for a really bad time because with 2 pair, we had 1 molecular geometry, right?
Yeah.
And then with 3 pair,
We have
We had 2 molecular geometries, and so naturally we're expecting 4 pair. We're going to have 3 molecular geometries, right? And with 4 pair, no, you essentially have 2 or 3. I'm sorry, you do have 3. So let's go to 5. How many do we expect for 5? 4 different kinds, right?
yeah.
Okay, so let's look at 5. So molecular geometry based on trigonal bipyramidal electron pair geometry, which means you have 5 pairs. So I'm going to make a little list of the molecular geometry. And we'll do different examples. So you could have a phosphorus.
Hydrogen?
Pardon me?
Never mind.
So we're going to do pH5.
Yeah.
So what do we call this molecular geometry? We call it trigonal bipyramidal. And the angles are 90, 120, and 180. Okay, so what happens if you have something different like, oh, I don't know. Let me think about this for a minute.
Seesaw?
Pardon me?
Seesaw?
Yeah, I'm just trying to think of the example that I want to use. Let's see. So for seesaw, we need 2, 4, 6, 8, 10 electrons. And 4 of them are going to come from hydrogens. So that means the other 6 have to come from the central atom. So we're going to do SH4.
Mm-hmm.
So here, this is the way we draw it. And notice the lone pair is equatorial. Now, why are they equatorial? It turns out that lone pairs repel better than bonding pairs. So you want to put those lone pairs as far away from the other pairs as is possible. If we put them on top here, you'd have 90-degree angles with 3 other atoms. If you put them here in an equatorial position, you only have 90-degree angles between 2 other atoms. And basically, that's how you look at it. How many 90-degree angles are there between the lone pair and the others? The fewer, the better. So here, 2 90 degrees, here 3 90 degrees. This is better by putting them here equatorial than axial. We call this seesaw. What are the angles? 90 degrees still, 120 still, and still 180. Okay, so now I got to come up with another one where we've got 10 electrons so that we have 5 pair. And you're only going to have 3 hydrogens, so that means the other 7 have to come from the central atom. So we're going to do this one. Chlorine, hydrogen, hydrogen, hydrogen. And notice I switched it and I put the hydrogen here on the right. You see that? And I put the lone pairs where the wedges and the dashes are. And the reason is because that's a lot easier to see what this is called. It's called T-shaped. So here you can see that if we look at this, it's kind of like this, right? And then if you rotate this guy 90 degrees, it's T-shaped. So it's an uppercase T, not a lowercase t.
Yeah.
And the angles are 90 degrees and 180 degrees. There's no longer a 120. And then there's one more. So in this one, we're going to do I3, -1. So I'm going to put that one over here. Actually, I'm going to do it right here because I can fit it in. So this is I3 -1. And this is linear. Because if you take a look, do you see this axial one that's going above and this axial one that's going below, right here and here?
Yeah.
And here and here, and here and here? I took these and I rotated them 90 degrees. So they're still here and here, above and below, but now they're side and side. So what is the angle here? 180 degrees. So the deal is when you have lone pairs, you put them in equatorial positions until they're filled. Okay? So here, we thought that maybe we'd have 4, and we do have 4 different geometries.
And there's 3 lone pairs.
Yeah, 1, 2, 3 on that iodine in the middle.
So for a total of 5.
So total of 5, because we have 5 pairs, that is, not lone pairs. 1, 2, 3, 4, 5. And now I guess with 6 pair, we're going to have 5 different geometries. So let's take a look at molecular geometry. Based on octahedral electron pair geometry, which means 6 pair.
Oh.
Right?
Yeah.
So the most common one is SH6.
Octahedral.
This one's called octahedral. And let's see. The angles are 90 degrees and 180 degrees. Okay, now I need to come up with an example where we have 12 electrons, but only 5 hydrogens. So that means that the central atom has to come up with 7 electrons. So I'm going to use something like chlorine. Now I can put that lone pair anywhere on chlorine. I could have put it on a wedge or a dash or up or below. I like to put it on the bottom because it looks a lot like what we call it, which is a square pyramid. Square pyramidal. And the angles are 90 degrees and 180 degrees. Now, another example would be a xenon with 4 hydrogens. Now, for the xenon, remember, lone pairs repel really well. If I'm going to put another lone pair on this guy, where am I going to put it? Am I going to put it on one of these places or up above if lone pairs repel really well?
On the side.
On the top, right?
Just opposite of each other.
Yeah, get them as far away apart from each other as possible. So I'm going to put the other lone pair on top. So what do we call this? Well, it's still a square, but it's a flat square, and we use the term planar. The angles here are 90 degrees and 180 degrees still. So we should have two more, right?
Yeah.
We don't. That's it. But you can imagine, though, if we did put another pair here, it'd have to be where one of these hydrogens goes, and it'd look like a T, wouldn't it? And then if we put another one down, it'd be opposite of the hydrogen and look linear. That's what we would expect. Okay, so those are all the molecular geometries you need to memorize. And as I took you through that journey, I tried to explain to you why they're going to be that shape, what the angles are, and you'll notice the angles always stay the same, right? There's only one time where the angles didn't stay the same, and that's right here. 5 pair. And the reason they didn't stay the same is not because we introduced new angles, but because some angles disappeared. The 120 disappeared. And then here, the 90 disappeared. So we didn't introduce new angles, we just got rid of some because they didn't exist anymore. Okay. So those are the molecular geometries you need to know based on your electron pair geometries. And you should be able to draw molecules. Okay? All right, let me put this away. Let's do some problems. How's that sound?
All right.
Okay, so last night I got to number 16, but didn't do it. So we're going to look at number 16. Determine the formal charge on each atom in the following molecules and ions. So to do this, you first have to get the Lewis structure, and then you go from there. So if we look at A and SO2, we get 6 plus 2 times 6, or 18 electrons. We're going to put sulfur in the middle because it can make more bonds than oxygen. So this is what it looks like to start with. And then we put lone pairs on each oxygen. When we're done with that, how many electrons have we used?
18?
16, right?
16.
8 and 8, 16.
Yep.
But we need to use 18. So where do we put the other 2 electrons?
The central atom.
Okay, there we go. But sulfur doesn't have an octet. So what do we do?
Make a double bond with one of the oxygens.
Right. Actually, it makes a double bond with both of them because this is one possibility. And this is the other possibility. What do we call these structures that look very similar, but kind of mirror images of one another?
Resonance.
Resonance structures. Okay, so let's assign formal charge on this oxygen.
Okay, hold on.
How many should it have? How many electrons should it have if it were neutral?
6.
6. How many does it have in this structure?
5.
6.
Okay.
1, 2, 3, 4, 5, 6. Each bond is 2 electrons, but the formality is, the formal rule is you only get half of the bonding electrons. So this oxygen should have 6 to be neutral. In this structure, it has 6, so its formal charge is 0. How about the sulfur in the middle? How many electrons should it have if it were just a neutral atom?
Is it 5?
Where's your periodic table? You shouldn't be doing this without your periodic table because during the test, you get to look at a periodic table. 6. In this structure, how many do we assign to this sulfur formally?
4.
1, 2, 3, 4, 5.
Oh, yeah, I wasn't looking at that one for some reason.
Okay, so if it's supposed to have 6, but it has 5, what's its charge?
+1.
How about this oxygen here? How many should it have if it were a neutral atom?
6.
How many does it have formally?
7.
7. So it's got 1 more than it should. What's its formal charge?
-1.
Okay, and look at these formal charges. They all add up to 0, which it should because this is neutral.
Right.
Now, the beautiful thing about this is we can just take these numbers and put them over here because when you have a single bond to this oxygen, it's a -1. So that's a -1. This is a +1, and this is a 0. So which one's better?
Either.
Neither. But here's the deal. Wouldn't this be better if they were all zeros?
Yeah.
Okay. How can we get this sulfur to have a 0 formal charge? And the answer is give it an electron. But we can't just give it 1 electron from anywhere. The best we can do is make a bond to that sulfur. And if we make a bond to it, it gets half of those, and therefore it has 6 electrons. What about this oxygen? It has 7 formal electrons. How can we make it have only 6 formal electrons?
Make a bond.
Take a lone pair and turn it into a bond. That way you're kind of giving 1 electron away and keeping 1, and now you have 7. So what about this? Formal charges are 0 everywhere. So which of these 3 is better?
The third one.
This one. It's so much better that if you have all zeros compared to something else having a non-zero, you choose the all zeros, no ifs, ands, or buts. Okay, so there is the structure of SO2, and there's the formal charges. How many pairs on that sulfur?
How many pairs
Yes, how many pairs?
or regions?
They're the same thing,
So 3.
3 pairs. So what is the orientation of those 3 pairs?
It would be trigonal planar
So like this,
or bent.
like that? The 3 pairs will be like that?
No.
The answer is yes.
Okay, so it is bent.
That's trigonal planar. We're talking about the pairs, not the molecular geometry. We're talking about pairs. So now when we fill in the rest, we ask ourselves, is that supposed to be a flat triangle or is it something else? And the answer is it's bent. And what are the angles?
120.
120. Okay, so let's put that one away. We assign formal charges and all that. Let's look at this next one. OSCl2, and remember, we're trying to get the formal charge on each. And since we just learned about molecular geometry, we're going for that too.
Okay.
So 6 plus 2 times 7 is 26 electrons. Who goes in the middle?
Oxygen.
Pardon me?
Oxygen.
Well, it's going to be sulfur or oxygen.
Right.
Because they both like to make 2 bonds, right?
Yeah.
When there's a tie, we then look at who can make more.
Would it be sulfur?
That's right. So sulfur's in the middle. So that's a good start. I like it because it's symmetrical. I like symmetrical looking molecules. I'm going to put electrons around oxygen first because it's the most electronegative, then the chlorines. And that's 24 electrons. So where do I put the last 2?
On sulfur.
There you go. Now we check for octets. Do we have them?
Yes.
Let's go with formal charges now.
Okay.
Once you've assigned them, you tell me, and then we'll compare our answers, okay? Is that what you got?
I wasn't done yet.
Oh.
Yeah.
I just saw you look up, so I thought maybe you were done.
Okay.
So the chlorines are zeros, the sulfur's +1, the oxygen's -1. So same question as before. I like zeros better. Is there a way, especially when you have a -1 and a +1 next to each other, to get them both to be zeros?
Double bond.
Yeah, so let's make a double bond between sulfur and oxygen. Still single bonds to the chlorines. And now they're all zeros, right?
Yeah.
So which one do we want? The one on the left or the one on the right?
On the right.
On the right. We're just going to cross out the one on the left. How many pairs on that sulfur?
4.
3.
Oh. Right. It doesn't have lone pairs anymore.
It doesn't have any lone. Oh, I'm sorry.
Or
It does
it?
have a lone pair. I didn't have it on mine. I goofed up. How many pairs on that sulfur?
4.
Okay, so we have to draw it so it looks kind of like this. Where do you think is the best place to put the lone pair? In my opinion, it's on top.
Okay.
And the reason for that is when you look at this, does it look like a 3-legged stool?
Yeah.
So 3-legged stool is trigonal, pyramidal. And what are the angles?
180.
Nope. What are the angles here when you have 4 pair?
You have 90 degrees.
Nope. Does that look like it's 90 degrees?
No, I was looking at the top right, but
That's the Lewis structure.
yeah, I know.
So you can't look at the Lewis structure for the angles. You have to look at this 3-dimensional drawing I have here. What are the angles?
120.
So 120 is when you have a perfect circle and you split it into 3 equal parts. We don't have that here. It's a radio station.
1095.
There you go. So there's that one. Now this looks like an interesting one because now we have 2 oxygens, right?
Yeah.
Let's check that one out. This should be fun. Let's see, that's 2 times 6 for the oxygens, right?
Mm-hmm.
6 for the sulfur, and 2 times 7 for the chlorines.
32.
Sounds right, 32 electrons, 14 plus 18, 32. Who's going to go in the middle?
Sulfur.
Okay, so I like it to look symmetrical, so I'm going to do this. Chlorines out on the sides and oxygens above and below. Or you could do oxygens on the sides and chlorines above and below. If you don't like it to be symmetrical like this, you can do something else. I don't care, but I like it to look symmetrical. Where am I going to put electrons first?
Oxygen.
That's right, because it's more electronegative. In fact, the most electronegative atom is fluorine, but the second most is oxygen. Okay, octets everywhere. Fantastic. And we've used 32, haven't we?
I don't know. I think I did it. I'm missing a pair. Oh, okay.
Well, how many around this chlorine?
8.
How many around the oxygen?
8.
There's 8 around each of the terminal atoms, right?
Yeah. 8 times
8
4.
times 4 is 32.
Okay.
So we don't have any more to deal with, right?
Right.
So they have octets everywhere, right?
Yeah.
Let's assign formal charges. When you're done, let me know. And in the meantime, I'm going to take a bite of my little pecan tart from Ramone's.
Okay, I think I'm done.
Okay, you get a 0 on chlorine, get a -1 on each oxygen, and you get a +2 on the sulfur.
Yeah.
This sucks big time. We never want a 2. We never want a +2. We never want a -2.
So can we have 2 double bonds to oxygen?
Right. We can make a double bond to the oxygen above. We can make a double bond to the oxygen below. And when we do that, they're all 0 formal charges. So no contest. The one on the right is what we choose. How many pairs on that sulfur in the Lewis structure?
4.
Great, 4 pair. So that means that sulfur is going to look kind of like this, right?
Tetrahedral.
Tetrahedral. But let's fill in the spaces. I think I want to put the oxygens like this. And the reason I want to put the oxygens here is because I wouldn't know how to make a double bond on the wedges. Do I do that? That looks kind of silly, doesn't it? And then this for the other one. Nah, I don't like that. But here, if I put the single bonded chlorines there, it looks pretty good. Don't you agree?
Yeah.
So my choice is to help me to make this look more clear. I'm going to put the chlorines on the wedge and the dash. And this is tetrahedral. And what are the tetrahedral bond angles again?
109.5.
109.5 degrees. And I swear, if you start saying 109.5, like it's a radio station, you'll remember it better. But if you make it dry like 109.5, you'll never remember it.
Sure, well.
109.5, smooth tetrahedral. Okay, so we only have one more to do. FSO3 negative. Okay, how many electrons?
Um, 31.
Let's see. I get 18 for the oxygens, another 6 for sulfur for 24, right? Another 7 for fluorine for 31, but that negative charge is a valence electron.
Oh, yeah. Good stuff.
So we get 32 electrons.
Right. Okay.
Okay. Fluorine makes 1 bond. Oxygen normally makes 2. Sulfur can make 2 normally. So who do we put in the middle?
Sulfur.
Sulfur. So normally if there's a tie break, you pick the one that's lower on the periodic table because they can make more bonds.
Yeah.
So we're going to put sulfur in the middle. And I'm going to put an oxygen on the left, one on the right, one below, and the fluorine up above. Where do we put our lone pairs first?
Oxygen.
Fluorine. It's the most electronegative.
Okay.
And then it doesn't matter which oxygen we start on. Now, here's something we have to understand. Because this has a negative charge on the molecule, which makes it an ion really, you will have to have at least one formal charge that'll be a -1. You can't get away with anything better than that.
Okay.
Okay. So what are the formal charges as it sits now?
The oxygens are -1, right?
Right.
So then sulfur is +2 then.
+2. And the fluorine?
-1.
It's actually a 0.
It's, yeah.
Because it has 7 as a neutral atom. And here we formally assign 7 to it. So
Yeah.
it's neutral.
Okay.
So we already know that there's a way to make that sulfur into a 0, make double bonds to the oxygens, right?
Right.
So we're going to do this. and we're going to judge it because that's what we do. We're judgy. I went ahead and made a double bond to every oxygen.
Okay.
Now let's assign formal charges.
So the oxygens are 0.
I like it. How about the sulfur?
0.
No.
9. Oh. Well, isn't it in group 6?
Yes.
Oh, and it has that, so -1.
Okay. And the fluorine?
0.
Okay. Now, what if we only made a double bond to one of the oxygens? What are the formal charges here?
So the single bonded oxygens are -1.
Okay.
The double bonded oxygen is 0.
Okay.
The sulfur is +2 again? No. It's +1.
+1.
Mm-hmm.
Because it should have 6, but it formally gets 5. So it doesn't have enough to be neutral. It's got to be +1.
Yeah.
And the fluorine?
0.
Okay. Now, a little bit of comforting realization is that when you add these formal charges together, what do you get? You get -1, and the charge on the ion is -1. So when you add up the formal charges, they should always equal the charge on this guy. So here, -1, -1, -1, +2, 0, that adds up to -1. That matches. Here you only have a -1. The rest are zeros. That adds up to -1. They all add up. Now let's try double bonds to 2 oxygens. What are the formal charges on this?
So the double bonded oxygens are 0. The single bonded is -1 still. The sulfur is 0. And so is the fluorine.
That's right. So there's only a -1 on this oxygen, right?
Yeah.
The others are zeros, which adds up to -1. So I like it. So which one do we like better? This one down here where the -1's on oxygen, or this one over here where the -1 is on sulfur? And here's the answer. We like the negative charge to be on the more electronegative atom. Between sulfur and oxygen, what's more electronegative? Well, fluorine is the most, oxygen's number 2, sulfur doesn't compare. So which do we like better? The one that I'm tapping or this one down here on the left? We like the one on the left. But is there a way of getting the -1 on the oxygen other ways? In other words, does this have resonance structures? And the answer is it does. Here's one way where the -1 is on this oxygen, not this one. And what's the third one going to look like?
Just changing the single bond to the right oxygen.
Correctamundo. Now, when we draw these, all three of these, we should do this also, the bracket, charge on the outside. Now, just looking at this, how many pairs on each of those resonance structures? How many here?
There's 4 pairs.
How many here?
4.
How many here?
4.
If they're resonance structures, the central atom should have the same number of pairs on each one. And they do. How many of these pairs are lone pairs on this sulfur?
None.
How many on this sulfur?
None.
And how many here?
None.
So that should also be the case. And so here we have 4 pair. What is the electron pair geometry going to be?
Tetrahedral.
Okay, and when we fill in the blanks, what are we going to call the molecular geometry? Since we have no lone pairs.
Tetrahedral.
Tetrahedral. So we don't want to draw this 3 times in 3D, but we can certainly do it once.
Okay.
And I'm going to put the double bonds like this, because it always looks better when the single bond is on the wedge and the dash. So there it is in 3D, it's tetrahedral. And what are the angles?
1095.
I didn't hear any joy in that 109.5. No joy.
And?
Well, you've ever heard of that Marie Kondo?
Yes.
Everything you keep in your life should bring joy to you. That's why I think you're going to lose that 109.5. I don't think it brings any joy to you.
I won't forget 1095 because I will never forget your radio station.
Okay. So I think we've done a pretty good job. We did a little extra work, right?
Yeah.
But we did reinforce the idea of molecular geometries and electron pair geometries. And that's a big part of the rest of the chapter. The one big thing you still need to learn is polarity. And it's not a big deal. It deals with electronegativities and whether one side of a bond is positive or negative. And then also whether one side of a molecule is positive and negative.
Yeah.
Yeah, or whether it's not positive and negative on the side to side. And what you learned in Chem 2 is the same thing we learned in Chem 1A for polarity.
So not really anything new there.
Nope. Do you remember Tony's way of assigning polarity?
No.
Draw the molecule in 3D. If there's an electronegative atom on one side of it, that's the negative side.
Oh, yeah.
And if you can't find an electronegative atom on one side, but they're evenly spread out or they're all in the center, it's nonpolar.
Right.
That easy. That easy.
Is this when we're also talking about the different types of bonds and which is stronger?
We're talking about different types of atoms so that the more electronegative atoms draw electrons to them.
We're not talking about different types of bonds yet, though.
You mean double, triple, singles?
Like hydrogen, nonpolar.
Oh,
Polar.
I'm not sure if we talk about that in this section. That was in Chem 2, but yeah. I don't know if we do that here in 1A. I'd have to look.
Okay.
So you're talking about hydrogen bonding, London dispersion forces, or are also called van der Waals forces, and dipole-dipole.
Yeah.
Yeah. We may talk about that, but that's pretty easy too. So you've done the hard work right now, and you just need to fine tune it.
Yeah. Okay.
All righty. You have a good rest of your day.
Thank you.
Bye-bye.